This is a very important topic. We are going to look at the Q/T ratio, and then this is followed by shearing stress for composite material. That's what I plan to cover. So where I finished off last Thursday, we are looking at this example. So we will still deal with this example. Okay, so I think I've uploaded the images on Avenue to Learn. If you all can go to Avenue to upload the files, okay, so when I'm doing this problem, you can see what we're trying to achieve down here. Right. So this problem over here, we are going to determine the stresses at point A and point B, right? So I want, rather than looking at stresses at just point A and point B, we are going to derive, okay, the shear stress distribution equation. Okay. So before I go on, on Thursday last week, we found that Vy is equal to 90 times 10 to the power 3 Newton. And we also, with this problem, we have found that the position of the centroid, which is Y bar, is 35 millimeters from the top. And I'm not going to waste time looking for second moment of area. Okay, I'm just going to write down the value, because second moment of area, you all know how to get the value easily. So if we have a transformation over here, this is our X, and this is our Y, and this is our rotation about Z. So from here, we know that this will be our Y, this is our Z, okay? So we know that over here, this is the position of our centroid. And we found that from the top is 35 millimeters. That we know already, okay? So IZZ, as I said, I don't want to waste time looking for the second moment of area, is 5.813 times 10 to the power minus 6, okay? So this example I'm going to show on more important is a shear stress distribution equation, okay? So the formula that we've been deriving our shear stress, okay, is shear stress is equal to VQ, for this case, Vy over IZZ QZ by T, okay? So the equation, of the shear stress is dependent on the thickness of the structure. And I'll elaborate this, what I mean by thickness of the structure, okay? So in general, we will formulate a piecewise equation that are dependent on thickness. Okay. And I'm going to show you what do I mean by this term over here. Okay. So now let's look at the cross-sectional view. Okay, so we're going to look at a cross-sectional view now. Okay, so knowing that the centroid, I'm going to sketch the centroid, that this is the position of our centroid. And we are aware that from the top, this distance over here is 35 millimeters. Okay, so what do I mean by piecewise equation? Okay, so we know that the thickness changes. Okay, so where the thickness changes is in two regions. Okay, so we know that over here the thickness, so I'll call this the flange. Okay, the flange. We know at the flange the thickness is equal to 0.16 meters. And we are also aware that for the web, right, the thickness now changed to, so it's twice, so it's 0.04 meters. So our piecewise equation is partitioned by the thickness of the cross section. Okay, so let me show you what I mean. So if we consider thickness is equal to 0.16 meters, right? The thickness is equal to 0.16 meters. Then the limits of our equation is from 0.015 meters, y, and it can go up to 0.035 meters. Okay, why is that? Because remember what we say, this is our datum, right? This point over here is our 35 millimeters, and this point over here is our 15 millimeters. Okay, so we're now going to formulate the shear stress distribution equation based on these limits. So this equation is only valid when y is greater than 0.015 meters and y is less than 0.035 meters. Okay, so let's look at our equation. Okay, so shear stress is equal to VQ over IT. And we are aware that V and I are constant. So it's a fixed value, which is given, so nothing to do. And we also know that for this case, thickness is equal to 0.16 meters. Okay, so the only thing that we have to formulate now is our what? Q. Okay, so now Q about the z-axis as a function of y now. Okay, so we know that this is equal to width, depth, y bar. Okay, so knowing that ZZ is our interest, axis of interest, we know that this is our width. And we are also aware that perpendicular geometry, this is our...
I'm sorry, Eugene.
Yes.
Why did we choose the thickness to be 0.16 and not 20?
Because the partition, okay, because the partitioning is controlled by the thickness. So this thickness over here where I highlight, the thickness is what? 0.16. Okay. The next change is the other one. The next change over here is this layer over here, which is equal to 0.04. Your equation is limited or is controlled by the thickness. Okay, you cannot form one equation that describes the entire cross-section area. You understand?
Yes, thank you.
Oh, and that is for that reason. Okay. So from here, right, we also know that our width is constant. Okay, so this is equal to 0.16. Our depth is varying, so it starts from 0.035 minus y, right? And that's the thickness. That's the depth, sorry. And then multiply by 0.035 plus by y and multiply by half. So this over here is your y bar. This term over here is your depth. and this term over here is your what? Thickness. Okay, and you've seen this before. I think we derived this, I think on week, is it Thursday? Let me see, is it Thursday where we start deriving? Yeah, it's over here. So remember, we formulate this expression over here, and this is what I've just applied. Okay, this is on last week on Thursday. This is what we applied. C minus y, C plus y multiplied by half. Okay, C means the C is the maximum distance relative from the centroid. That's why the analysis starts from what? Starts from y max. Okay, right. We choose 0.035 because this is the upper limit over here. Okay, so from here, we just now need to get our value. So let me get my calculator. So 0.035 squared times by 0.5 times by 0.16 is equal to 98 times 10 to the power minus 6 minus by 0.16 times by 0.5, 0.08 y squared. And the units over here is in meter cube. Okay, it's best to do everything in meter cube now. Okay, so once we have this, okay, so we immediately put into the formula that shear xy, okay, as a function of y. Now, why shear xy? Okay, so let me explain why shear xy. Okay, so if we look at the face. Okay, so if now I were to construct this in 3D, okay, if I would draw this in 3D. Okay, so now I'm constructing this in 3D. And this is our X, Y, and this is our Z. This plane over here, right? This plane over here will intersect the what? Will intersect the Z-axis, X-axis. Okay, so that's why you have shear. The intersecting is X, and then the shear force Vy will generate a shear stress flowing down in this direction, or the shear flow will be coming down in this direction. Okay, so this is why this is our Y. Okay, so this is our intersecting plane. And this is the direction of shear flow or shear stress. So from here, we know that this will be equal to Vy over Izz, Qz over T. Okay, so Vy over here, we know that this is 90 times 10 to the power 3. This is 98 times 10 to the power minus 6. This is your Q minus by 0.08 y squared. And then we divide by Izz. So Izz given to us 5.813. And then the thickness is equal to 0.16. Okay. So this will be equal to 90 power 3 times 98 power minus 6 divided by 5.813 power minus 6 divided by 0.16. So it's equal to 9.483 times 10 to the power 6. And then minus by times by 0.08, 7.741 times 10 to the power 9 y squared. Okay. So now, the question that we tend to ask ourselves is, how do we know that this equation is correct or wrong? Right? How do we know? Anyone? How